Okay, in the first video on redox, we established basic definitions and I taught the viewer how to look at a chemical equation like the one that is displayed here, how to look at and determine individual oxidation numbers and formal charges so that we could figure out whether or not electrons had been transferred. And what I want to do in this video is practice this concept with some other chemical reactions so that we can so that you can firm up the concept. What I want to do is start the discussion though by talking about determining the oxidation number within a molecule. I want to revisit that issue for a moment. So if we look at the SO2, in the last video I defined oxidation number in part as being a theoretical value that's determined by electronegativity difference. And I showed the viewer how to set up an equation to solve for an unknown. So I want to address that concept in a little bit more detail here. So what do I mean by this electronegativity difference? All right, so in the case of SO2, and for that matter, similarly with the SO3, we have sulfur and oxygen that are bonded together. Now, oxygen is a more electronegative atom than sulfur. So in the bonding between these two atoms, oxygen is going to own the majority of the electron density. And that electron density is going to translate into a charge that's going to be somewhere very close to, or I should say, that's going to translate into an oxidation number, right? It's not really a formal charge on the oxygen here, but the electron density is going to result in a partial charge on the oxygen that's going to be somewhere close to -2 because of the electronegativity difference between the oxygen and the sulfur. So we're approximating what the charge would be on the oxygen. The fact that the sum total of all these differences in the molecule needs to be 0 is what allows us to set up this convenient little equation. So we write 0 here. And then we really don't know what the oxidation number or the charge is on the sulfur, but we can approximate it because we know pretty much that the electron density is going to be residing with the oxygen, and we know approximately how much of that density is going to be there. So all we have to do then is look at the molecule, and the last little bit is figuring out what the total net charge is going to be on the oxygen. And because there are two oxygens, all right, we can figure that's going to be around -4. So that's what allows us to then set up this little equation where we then could solve for the approximate value on the sulfur. And then by comparing that to what we get on the sulfur in the SO3, then we were able to ascertain that electrons had indeed been transferred from one component in this reaction to another. And so we were able to say, yeah, that's a redox reaction, that in fact the SO2 is oxidized because this guy here is going to go, it ends up being +6. This is oxidized, the oxygen is reduced, and electrons are transferred from the SO2 to the oxygen. All right, so let's practice this now, this idea with some other equations. So the first one I want to tackle is the combustion reaction between methane and oxygen. All right, and we're also going to have a 2 right here to balance the equation. So now, again, applying the principles we learned in the last video, first thing to notice is that we got an oxygen here which is in its elemental form, O2. So it's in the category where the oxidation number is going to be 0. So let's go ahead and put it in for that. We then have the methane. And in terms of the methane, in the vast majority of cases, hydrogen, when paired with something else, is always going to be +1. Most of the time. There are some exceptions, but I don't want to get tied down in that in this video. So maybe we'll have a third video where we look at some of these more difficult areas. But for now, You can most of the time assume when you see hydrogen, it's going to be +1. All right, so I'm going to go ahead and put that in. Now, there are 4 hydrogens in this molecule, so the total net is going to be equal to +4 for the hydrogen, and that leaves the carbon as an unknown. Using the same technique that we used for the SO2, all right, we're going to come over here for the methane, and we're going to say, okay, carbon is the unknown. There's only one of them. And we know that the total hydrogen is going to equal 4. We set the whole thing equal to 0. So the net, or not the net, the oxidation number, therefore, on the carbon is going to be -4. -4 for the carbon. Now we come over here to the water and the CO2. Let's deal with the CO2 first. Again, for the oxygen, in the vast majority of situations, it's going to be -2. Since there are 2 oxygens in CO2, the net on the oxygen in the compound is going to be -4. So to find the carbon, we set up our equation. It's going to be C -4 is equal to 0. So my carbon is going to be +4. Notice that we went from -4 to +4. So right now we know that this is, yes, it's a redox. So we know electrons have definitely been transferred. The only way in the carbon that we could go from -4 to +4 is by the loss of electrons. I'm going to write that down. The loss of electrons is being demonstrated right here. Loss of electrons. All right. So the CH4 is being oxidized. Oxidized. Now, the oxygen, let's deal with that. We see the oxygen is going from an oxidation number of 0 on the left side of my equation to -2 for this oxygen in CO2 and -2 for the oxygen in the water. So the only way that can happen is for the oxygen to be gaining electrons. So my oxygen had to gain electrons. Gain electrons. Let me put that in. So this is going to gain gaining electrons. All right. Gaining electrons. All right, so that means that the oxygen, let me get a different color here. The oxygen is reduced. Reduced. All right. Now, let's look at another example. And I'm going to pick an equation here that, what I'm trying to do is pick equations for the viewer that are not immediately obvious when you look at them, because those are the hard ones. If we have time, I'll do a third example here, and we'll do an obvious one so that you know what I'm talking about. Now, for this equation, first thing you should do is go through and identify elemental components, because you know that these are going to be 0. So this has an oxidation number of 0. We look at the O3 and we go, uh-oh, what do we do about that? Well, look what I added here. See, here's O3, and it gets a 0 because O3 is what we call, O3 is what we call an allotrope. Okay, so this is what we call an allotrope. And an allotrope simply means this is an element with more than one natural form. So in the case of oxygen, we have O2 and we have O3. Two natural forms of this. So guess what? This gets an oxidation number of 0. So now we need to look at the other components. So again, what we want to do is apply what we learned in the past two problems. So we know that the oxygen here is going to be -2. That leaves the nitrogen. Simple equation, the nitrogen is going to be N, and then we're going to be -2 equals 0. So the N in NO is going to equal +2. All right, and that only leaves the N in NO2. Again, in the NO2, the oxygen is -2. All right, and there's two of these. So the net is going to be a total of -4. So we're going to have N -4 is equal to 0, or N is equal to +4. So let's see if we can figure out what happened. Well, A number 1, this is definitely oxidation reduction, because there's definitely a change. We're going from +2 on the nitrogen to +4. So electrons had to have been manipulated here. What exactly happened? Well, we went from +2 to +4. The only way that that could happen would be through the loss of electrons. So we've had loss of electrons in this example. All right, and then the oxygen goes from 0 in O3 to 0 in O2. No change between these two, but check it out. See, we went from O0 here to O -2 in at least one of the components. So the oxygen, the only way the oxygen could go from 0 to -2 is through the gain of electrons. So let's see, let me put an arrow here and to over here, and we had the gain of electrons. All right, so the NO here was oxidized, and the O3 here was reduced. All right, now I think we got room for one of my obvious examples. All right, so let's put this in here. We're going to have zinc metal reacting with hydrochloric acid to produce zinc chloride, aqueous, and hydrogen gas. Now, these kinds of equations are easier to figure out because, look, we're going from the natural metal, which we know is 0, to an aqueous solution of zinc chloride. So the zinc here has to be ionized. It's +2. All right, and then the hydrochloric acid, the hydrogen is +1, has to be. All right, and the Cl in this case is ionized, so it is Cl -1. On this side of the equation, we see the Cl is maintained at -1. It's not changing. However, the hydrogen gas goes to 0, or the hydrogen goes to 0 once it's formed hydrogen gas. So you can see that the zinc is going from the metal to the ionized form of the metal, and the hydrogen is going from being ionized to being in its elemental form, where the oxidation number is 0. So the metal is oxidized. So okay, backing off a step. Yes, this is redox. Right, the zinc is being oxidized, and the hydrochloric acid is being reduced. Specifically, the hydrogen in the hydrochloric acid is reduced to the gas. And coming back over here to finish, yes, this was redox, the big picture view. All right? Okay.